December 1942, Toledo, Ohio. The temperature inside the Willys-Overland plant hovers at 98 degrees Fahrenheit, despite the snow falling softly outside. Steam hisses from hydraulic presses calibrated to exert exactly 12,000 pounds of force per square inch. Metal strikes metal with metronomic precision. A Jeep olive drab chassis number stamped 201-67455 rolls off the line under arc lights that burn at 2800 lumens. 4 minutes pass, another follows, then another. Beyond these walls, armies move across 3 continents, burning fuel, wearing down machinery, demanding replacement at rates that would have seemed impossible just 18 months prior. Inside, 3,000 workers, welders, machinists, inspectors, drivers, fight a different kind of battle. They are armed not with rifles, but with torque wrenches, calibrated to 35 foot-pounds, with steel dies machined to tolerances of 5/1000ths of an inch. This is not merely a story of production. This is the mathematics of industrial warfare made manifest. The transformation began not with a declaration of war, but with a radio address delivered on the 29th of December 1940. Franklin Delano Roosevelt, speaking from the White House diplomatic reception room, articulated a vision that would require the complete restructuring of American industrial capacity. "We must be the great arsenal of democracy," he declared, his voice transmitted across 950 commercial radio stations to an estimated 60 million listeners. The challenge implicit in those words represented perhaps the most audacious industrial mobilization in recorded human history: the conversion of an entire peacetime manufacturing infrastructure into a war production apparatus operating at scales that exceeded existing theoretical models of industrial output. Before the 7th of December 1941, the Willys-Overland plant in Toledo occupied 375,000 square feet of manufacturing space dedicated to civilian automotive production. Annual output averaged 3,1000 sedans, the Willys America, a modest vehicle retailing at $525, equipped with a 134 cubic inch L-head engine producing 63 horsepower. Chrome bumpers, civilian paint schemes, leather upholstery options. The production tempo followed peacetime rhythms, 8-hour shifts, quality control prioritized over speed tooling, optimized for variety rather than standardization. The United States Army's July 1940 request for proposals fundamentally altered these parameters. The specification document, distributed to 135 automotive manufacturers, outlined requirements for what military procurement officers termed a light reconnaissance vehicle, a quarter-ton truck capable of traversing terrain, inaccessible to conventional transport, powered by an engine generating sufficient torque for 30-degree inclines while maintaining a loaded weight below 1,300 pounds. Maximum speed 50 miles per hour. Fuel economy minimum 20 miles per gallon. Production timeline 75 days from contract award to first prototype delivery. 132 companies declined. The engineering challenges appeared insurmountable simultaneously. Achieving lightweight construction, structural durability, and mass production viability contradicted fundamental automotive design principles. 3 firms accepted: American Bantam Car Company, Willys-Overland Motors, and Ford Motor Company. What emerged from their competitive prototyping would become more than a military vehicle. It would represent a convergence of industrial engineering, metallurgical innovation, and manufacturing process optimization that redefined the relationship between design complexity and production velocity. The central question crystallized: how does an industrial system reconfigure itself to produce not what is profitable, but what is necessary, and to do so at rates that exceed all historical precedent? The competitive evaluation process commenced on the 11th of July 1940 at Camp Holabird, Maryland, where the Army's Quartermaster Corps established quantitative testing protocols unprecedented in military procurement history. Each prototype would undergo 3732 individual performance assessments across 16 categories, gradient climbing capacity measured at intervals from 15 to 60 degrees, suspension articulation tested across 127 distinct obstacle configurations, powertrain durability, evaluated through continuous operation cycles, exceeding 5,000 miles under combat simulated loads. American Bantam delivered first. Their prototype, designated the BRC-60, weighed 1,850 pounds, 38% over specification, but demonstrated superior maneuverability through its 60-inch track width and 79.75-inch wheelbase. The engineering team, led by Carl Probst, working from a single drafting table in Butler, Pennsylvania, had completed the design in precisely 147 hours. Yet Bantam's manufacturing capacity remained catastrophically insufficient, maximum annual production potential of 2,100 units against projected military requirements, exceeding 15,000 vehicles. Willys-Overland's submission, the quad prototype, introduced a critical innovation that would prove decisive. Chief Engineer Delmar Barney Roos had specified a Go Devil engine, a 134 2-cubic-inch inline 4-cylinder power plant generating 60 horsepower at 3,600 revolutions per minute, producing 105 pound-feet of torque at 20 revolutions per minute. This represented a 41% increase in power-to-weight ratio compared to Bantam's Continental engine. During gradient testing at a consistent 27-degree incline, the quad maintained velocity while carrying a 600-pound payload, a performance margin exceeding requirements by 23%. Ford's entry, the GP Government P model, leveraged the corporation's unmatched production infrastructure, 117 manufacturing facilities, 142,000 employees, vertical integration, encompassing everything from ORE, processing to final assembly. Yet their initial prototype, delivered the 23rd of November 1940, incorporated numerous proprietary Ford components incompatible with the emerging standardization framework, a strategic miscalculation that would require extensive redesign iterations. The Army's selection criteria evolved beyond mere performance metrics to incorporate what procurement analysts termed production scalability coefficients, quantitative assessments of each manufacturer's capacity to transition from prototype to mass production while maintaining tolerances within acceptable variance thresholds. Willys demonstrated superior readiness. Existing Toledo plant infrastructure required only 31% retooling compared to Ford's estimated 64% facility conversion rate. The company's experience manufacturing the America sedan meant they possessed forge presses already calibrated for automotive-grade steel, forming heat treatment furnaces capable of processing 18 tons of components, 8-hour shift, and a skilled workforce familiar with precision assembly protocols. November 1941 marked the pivotal decision point. The War Department awarded Willys-Overland the primary production contract for what would be designated the MB model military specification, Willys B Series. Simultaneously recognizing that no single manufacturer could meet projected demand curves, they contracted Ford to produce an functionally identical variant, the GPW, using Willys blueprints. This represented a revolutionary approach to military procurement, standardized specifications, shared across competing manufacturers, every component engineered for interchangeability, down to individual fasteners. The standardization philosophy extended to molecular-level precision. Each MB GPW featured 5, 6, 7, 7 individual parts, every one documented in specification sheets, defining not merely dimensional tolerances but material composition requirements, spring steel containing 0.55 to 0. 65% carbon content cylinder blocks cast from grey iron with minimum Brinell hardness of 187, electrical wiring, insulated with rubber compounds resistant to temperature fluctuations from -40 to +160 degrees Fahrenheit. This granular standardization enabled battlefield logistics personnel to cannibalize damaged vehicles for functional components, creating a self-sustaining repair ecosystem that reduced replacement demand by an estimated 5%. The mathematics of military-industrial efficiency had been established. Design complexity would be sacrificed for production velocity. Aesthetic considerations eliminated entirely. Every engineering decision filtered through a single criterion. Can this be manufactured at scale, maintained under field conditions, and replaced rapidly when destroyed? The blueprint was complete. Now, the machinery of mass production required activation. The 17th of January 1942, The transition order arrived at the Toledo facility at 0647 hours, a Western Union telegram containing Production Directive WPBL 41, authorizing the cessation of all civilian automotive manufacturing and immediate conversion to military specification output. The olfactory signature of the plant shifted within 72 hours. The acrid sweet aroma of civilian automotive lacquer, containing 42% nitrocellulose, 31% alkyd resins, replaced by the sharper chemical profile as military-grade primer, formulated with zinc chromate corrosion inhibitors and pigments engineered for minimum solar reflectivity across wavelengths from 400 to 700 nanometers. The retooling process represented an exercise in industrial metamorphosis operating under constraints that defied conventional manufacturing economics. Willys-Overland engineers documented 1847 individual equipment modifications required to transition from Americar sedan production to MB Jeep assembly. Stamping presses calibrated for civilian body panels, requiring 2,300 pounds per square inch for forming compound curves in decorative fenders, underwent hydraulic recalibration to 8,700 pounds per square inches for military specification. Flat plane components, prioritizing structural integrity over aesthetic consideration. Die sets weighing 14 tons, each machined from tool steel at costs exceeding $31,000 per unit, were removed via overhead crane assemblies and replaced with military tooling delivered from subcontractors operating across 17 states. The workforce transformation occurred with velocity that suggested systemic organizational capabilities exceeding peacetime operational parameters. December, 1,941 employment records documented 4,217 workers, 91% male, average age 34. 2 years, 73% possessing automotive manufacturing experience, averaging 6.8 years. By March 1942, total employment reached 8,946, a 112% increase achieved through recruitment protocols, targeting demographics previously excluded from industrial labor markets. Women constituted 37% of new hires, African Americans, 18%, rural migrants from Appalachian regions, 23%. Training programs compressed skill acquisition timelines from the peacetime standard of 180 days to emergency protocols, requiring 21 days for basic station competency, 47 days for precision operations, including welding, certification to American Welding Society standards. The assembly line architecture embodied principles of temporal optimization that would later be codified in industrial engineering literature as takt-time synchronization, German terminology adopted ironically, given the geopolitical context. Production flow divided into 24 discrete stations, each allocated precisely 240 seconds, with buffer intervals of 15 seconds between stations to accommodate variance in human performance rhythms. Station 1 frame assembly, where workers positioned 0.12-inch channel steel rails onto jigs, maintaining parallelism within 0.015-inch tolerance. Station 8 engine mounting, requiring torque sequences following predetermined patterns. Bell housing bolts tightened to 35 foot-pounds in star configuration to prevent crankcase warping. Station 17 electrical harness installation, where color-coded wiring read for positive 12-volt circuits, black for ground returns, yellow for lighting systems, followed routing diagrams specifying minimum bend radii 1.5 inches to prevent conductor fatigue. The acoustic environment reflected this mechanized choreography. Ambient sound pressure levels measured 94 decibels at worker ear height, equivalent to operating a chainsaw at 3-foot distance sustained across 10-hour shifts. Pneumatic rivet guns firing at 2,400 impacts per minute created percussive patterns, synchronized to conveyor advancement. Overhead crane warning bells operated at 1200 Hz, a frequency selected for maximum intelligibility above industrial background noise. Workers developed communication protocols reliant on hand signals, closed fist, indicating stop command, circular arm motion, signaling crane approach, thumbs up, confirming torque specification compliance. Thermal conditions inside the facility ranged from 62 degrees Fahrenheit in January ambient to 112 degrees in summer months, near heat treatment furnaces operating at 1550 degrees for spring steel. Tempering. Ventilation systems moved 340,000 cubic feet of air per minute through ductwork, yet temperature gradients between stations varied by 37 degrees, creating microclimates that workers navigated through spatial memory and experience. By August 1943, daily output stabilized at 563 vehicles, a production rate representing 99.2% of theoretical maximum capacity given existing infrastructure constraints. They called it the industrial heartbeat. Every 240 seconds, a completed vehicle emerged from Station 24, where final inspection protocols required 93 distinct verification points executed by quality control personnel trained to detect deviations. Invisible to untrained observation, brake pedal free play, exceeding 0.75 inches, steering wheel rotation resistance outside the 12 to 18 pound specification range, tire pressure variance beyond plus or minus 2 psi from the mandated 28 pound threshold. This was not mere assembly line production. This was the materialization of what industrial theorists would later codify as continuous flow manufacturing, a production philosophy where temporal precision superseded all other operational variables. The conveyor system itself represented an engineering marvel, calibrated to tolerances that would have seemed excessive in peacetime contexts. The primary assembly line stretched 1847 feet, powered by a 15-horsepower electric motor, driving a roller chain mechanism through a 471 reduction gearbox, advancing at precisely 7.7 feet per minute, a velocity calculated to provide each station its allocated 4-minute interval. Secondary feeder conveyors, 43 in total, delivered subassemblies on trajectories synchronized to intersect the primary line with temporal precision of plus or minus 3 seconds. A differential gear assembly, pre-lubricated with SAE 90 hypoid gear oil and torqued to specification at a satellite workstation 280 feet distant, would arrive at Station 11 at the exact moment a chassis reached the corresponding installation point. The mathematical architecture underlying this choreography revealed industrial optimization principles that transcended mere automotive manufacturing. Engineers had calculated optimal station loading through time-motion studies documenting 6847 individual worker movements, measuring each action in units called thurbligs, a time measurement system developed by efficiency expert Frank Gilbreth, quantifying human motion down to 1/18 of a minute. Reach for wrench 0.036 minutes. Position bolt 0.042 minutes. Apply torque to specification 0.128 minutes. These granular measurements enabled workload distribution, ensuring no station operated below 91% efficiency or exceeded 103% of theoretical capacity, a variance range, preventing both idle time and bottleneck formation. The sensory environment inside this mechanized ecosystem defied conventional descriptive frameworks. Welding stations generated ultraviolet radiation at wavelengths requiring protective eyewear rated to shade number 10, blocking 99.997% of harmful frequencies. The sharp ozone odor produced by electrical arc welding oxygen molecules split into reactive atomic oxygen by 7000 degree plasma temperatures mixed with vaporized metal particulates suspended at concentrations measured at 4.7 milligrams per cubic meter just below the threshold, requiring supplementary ventilation protocols. Hydraulic systems operated at 100 pounds per square inches, their rhythmic cycling creating pressure waves perceptible as low-frequency vibrations transmitted through concrete floors, engineered to support dynamic loads of 850 pounds per square foot. Workers developed an almost subconscious awareness of the production rhythm. Veteran assemblers could identify deviation from optimal tempo through subtle acoustic cues, a rivet gun firing 17 milliseconds, later conveyor motor laboring under slightly excessive load, a torque wrench clicking at fractionally incorrect pitch, indicating calibration drift. This represented human adaptation to machine temporality, where biological rhythms synchronized with mechanical cycles through daily exposure, averaging 600 production iterations per shift. The statistical outputs validated the system's effectiveness with quantitative certainty. Daily production logs from November 1943 documented output variance of just 2.7% across 30-day periods, 563 vehicles on average, minimum 547, maximum 578. This consistency occurred despite workforce turnover rates of 8% monthly material supply disruptions, affecting 14 separate component categories, and seasonal temperature fluctuations, requiring recalibration of hydraulic fluid viscosity to maintain pressure consistency. Annual production for 1,943 reached 137,896 vehicles from Toledo operations alone, representing 377 Jeeps daily, when accounting for scheduled maintenance shutdowns, a production density of 0.37 vehicles per 1,000 square feet of manufacturing space efficiency metrics, unprecedented in automotive history. The factory had evolved beyond mere manufacturing infrastructure. It had become a living demonstration of industrial capacity transformed into strategic weapon proof that organizational precision could generate material abundance at scales previously confined to theoretical projection. The human infrastructure supporting this industrial apparatus revealed organizational dynamics that contradicted conventional labor economics. Personnel records from March 1943 documented workforce demographics, representing a fundamental restructuring of American industrial participation. 3312 women, employed in roles previously restricted to male workers, performing operations requiring identical technical competency, TIG welding certification, blueprint interpretation, precision measurement using micrometers calibrated to 0.001-inch resolution. This demographic transformation occurred not through ideological commitment to gender equity, but through mathematical necessity, projected male workforce availability, accounting for military conscription rates, and competing defense industry. Demand yielded a labor shortage of 4,100 workers by June 1942. The solution emerged from pragmatic calculation rather than social progress. Mary Catherine Brown, employee number 18447, represented this systemic reconfiguration. Age 23, prior employment history, limited to textile manufacturing at $0.42 per hour. She completed acetylene welding certification in 19 days, 7 days below program average. Her station number 14 required joining frame components using gas metal arc welding at 180 amperes, maintaining electrode angles between 15 and 20 degrees, producing beads with penetration depth of 0.156 inches minimum to achieve tensile strength, exceeding 70 pounds per square inches. Performance evaluations from August 1943 rated her productivity at 104.7% of station quota, 417 welds per shift, against the standard 398 with defect rates of 1.2% compared to facility. Average of 1.8%. James Carter, employee designation 20891, enlisted at age 17 through documentation, later revealed to contain age misrepresentation, a common practice given that 14% of wartime industrial workers were subsequently discovered to be below the legal employment age of 18. Assigned as line apprentice to Station 7 transmission installation, requiring torque sequences of 19 separate fasteners to specifications, ranging from 22 to 48 foot-pounds, he demonstrated learning curve acceleration characteristic of neuroplasticity advantages in adolescent workers. Training completion occurred in 16 days. Performance optimization reached 97% of veteran worker productivity within 43 days of initial employment. The physiological demands of sustained industrial labor operated at thresholds approaching human performance limits. Shift durations extended to 12 hours during peak production periods from July 1943 through January 1944, with 6-day work weeks representing standard scheduling. Metabolic studies conducted by Army medical personnel embedded within industrial facilities measured caloric expenditure, averaging 3,847 calories per 12-hour shift for assembly line workers comparable to agricultural labor during harvest operations. Ambient temperature conditions in heat treatment areas reached 108 degrees Fahrenheit, creating core body temperature elevations requiring hydration protocols of minimum 3.2 liters of water per shift to prevent performance degradation from dehydration-induced cognitive impairment. The psychological architecture sustaining this operational tempo incorporated mechanisms beyond mere patriotic motivation. Factory management implemented feedback systems providing direct linkage between individual effort and battlefield outcomes. Letters from military personnel overseas describing specific instances where Jeep reliability affected mission. Success rates were reproduced and distributed through facility bulletin boards. One correspondence dated the 14th of October 1943 from First Lieutenant Robert Matthews, stationed with the 82nd Airborne Division in Sicily, described a Jeep bearing serial number MB 427-819 that sustained operational capability despite sustaining small arms fire, penetrating the engine block, allowing evacuation of wounded personnel across 14.7 miles of contested terrain. This vehicle had been assembled during third shift operations on the 27th of March 1943. Workers on that shift received copies of the letter, creating psychological connections between abstract production quotas and tangible human outcomes. The systemic result manifested in retention rates, defying conventional industrial labor patterns. Monthly workforce turnover averaged 8.2% in Toledo operations, compared to 14.7% across comparable manufacturing facilities. This differential, seemingly modest, translated to retention of institutional knowledge and maintenance of skill distribution curves that preserved production consistency. The operational validation of industrial capacity occurred not in factory performance metrics, but in field deployment across geographically dispersed theaters, presenting fundamentally distinct logistical challenges. The first combat deployment of MB series vehicles occurred the 8th of November 1942 during Operation Torch, the Allied invasion of North Africa, where 12847 Jeeps participated in amphibious landings across 3 separate beachheads spanning 876 miles of Moroccan and Algerian coastline. The environmental parameters exceeded design specifications established during temperate zone testing, ambient temperatures reaching 127 degrees Fahrenheit, sand particulate concentrations of 2,300 milligrams per cubic meter, creating abrasive conditions that degraded piston ring tolerances terrain, consisting of unconsolidated sediments, requiring continuous four-wheel drive operation at fuel consumption rates 34% above standard. Estimates. Performance data collected by Army Ordnance Department field evaluation teams revealed operational characteristics that validated the standardization philosophy underlying mass production design decisions. Mean time between failure intervals averaged 1,847 miles under combat conditions, a reliability threshold, enabling tactical deployment patterns previously impossible with conventional wheeled transport. The vehicle's power-to-weight ratio of 46. 3 horsepower per ton permitted gradient climbing of 31 degrees, while carrying 800-pound payloads, enabling supply line operations across mountainous terrain in the Tunisian campaign, where conventional trucks required winch-assisted towing or complete route abandonment. The Pacific Theater presented inverse environmental challenges, demanding different performance parameters. Deployment to Guadalcanal, beginning August 1942, introduced operational conditions characterized by humidity levels averaging 89% rainfall accumulations, exceeding 240 inches annually, and terrain consisting of decomposed volcanic soils with load-bearing capacity insufficient for vehicles exceeding 1.2 tons per axle. The Jeep's 2,450-pound curb weight, 49% below the light truck classification threshold, enabled mobility through terrain that immobilized heavier logistics vehicles. Field modification protocols emerged through decentralized innovation, jungle canopies fabricated from salvaged parachute material, waterproofing enhancements using rubberized canvas treated with neoprene compounds, engine air intake, extensions elevated to 42 inches above ground level, preventing water ingestion during river fording operations, documented at depths reaching 36 inches. The European campaign introduced the vehicle into combined arms operations, where mobility integration with mechanized infantry tactics created tactical flexibility unprecedented in military doctrine evolution. Following the Normandy landings of the 6th of June 1944, where 14621 Jeeps landed during the first 30 days of operations, The vehicle enabled reconnaissance protocols extending 7 miles ahead of main force elements, a standoff distance providing advance warning of German defensive positions that reduced infantry casualty rates by estimated margins of 1.824%, according to post-battle analysis, conducted by Army Historical Divisions. General Dwight Eisenhower's assessment, documented in his post-war memoir, Crusade in Europe, published 1948, characterized the Jeep as one of the 3 decisive weapons of World War II, alongside the C-47 transport aircraft and the atomic bomb, a technological triumvirate representing mobility, logistics reach, and ultimate destructive capacity. This evaluation reflected strategic-level recognition that industrial capacity to produce reliable mechanical systems at scale constituted a force multiplier exceeding the tactical value of individual weapons platforms. Statistical analysis validated this assessment. The 6.39245 Jeeps deployed across all theaters transported an estimated 2.8 billion ton-miles of supplies and personnel between 1,942 and 1,945, creating logistics throughput that enabled offensive operations, maintaining momentum across advance rates averaging 4.7 miles per day. During the Western European campaign, velocity figures, unprecedented in military history prior to mechanized warfare doctrine. The symbolic dimensions transcended functional utility. To Allied personnel, the vehicle represented tangible evidence of American industrial capacity, each Jeep serving as physical manifestation of a productive apparatus capable of generating material abundance at scales the Axis powers could not replicate. German military intelligence estimates captured post-war from Wehrmacht logistics planning documents reveal systematic underestimation of Allied vehicle replacement rates, with projections assuming maximum Jeep production of 180,000 units annually versus actual output exceeding 490 inches, 1,943 alone. The industrial coordination mechanisms underlying Jeep production represented a fundamental reorganization of capitalist competition dynamics, transforming proprietary advantage into collaborative standardization protocols unprecedented in American manufacturing history. Prior to wartime mobilization, automotive patent portfolios constituted strategic assets defended through litigation. Ford Motor Company maintained 1847 active patents as of January 1941. Willys-Overland held 312. Chrysler Corporation controlled 2104. These intellectual property frameworks generated competitive moats preventing component interchangeability. A Ford crankshaft bearing measured 2.498 inches in diameter, while Willys specifications called for 2.501 inches, a variance of 0.003 inches, sufficient to prevent cross-manufacturer compatibility, thereby locking consumers into brand-specific parts ecosystems, generating sustained revenue through captive replacement markets. The War Production Board Directive WPB 125, issued the 18th of March 1942, mandated complete technical specification sharing across all Jeep manufacturers, effectively nationalizing private intellectual property for duration of hostilities. Ford engineers received complete access to Willys blueprints covering 5, 6, 7, 7 components, including proprietary innovations in transfer case design, where Willys had achieved a 17% reduction in gear tooth stress concentrations through modified involute profile geometry. Reciprocally, Ford shared advances in electrical system voltage regulation. Their generator design maintained output stability within plus or minus 0.3 volts across engine speeds from 800 to 40 revolutions per minute, compared to Willys' variants of 0.7 volts, representing measurable improvement in electrical component longevity. The resulting standardization architecture operated at levels of precision that transformed interchangeability from aspiration to engineering mandate. Every fastener thread pitch standardized to unified thread standard specifications 7. 16-inch bolts required exactly 14 threads per inch machined to class 2, a tolerance allowing maximum pitch diameter variance of 0.0015 inches. This granular standardization extended to metallurgical composition, Spring steel specifications mandated 0.6% carbon content with variance tolerance of plus or minus 0.05%, silicon content between 0.5–0.35% manganese, 0.50–0.8%. Such precision enabled battlefield logistics personnel to cannibalize components from vehicles manufactured by different contractors. A Ford GPW transmission could be installed in a Willys MB chassis with zero modification, reducing mean time to repair from 14.7 hours to 3.2 hours, according to field maintenance data compiled by Ordnance Department Technical Services. American Bantam Car Company's role in this industrial ecosystem revealed the paradoxical dynamics of innovation versus production capacity. Bantam engineer Karl Probst had originated the fundamental Jeep architecture in July 1940, completing initial design specifications in 147 hours, a creative achievement that established the conceptual framework subsequently adopted by larger manufacturers. Yet, Bantam's production infrastructure could not scale beyond 2, 3, 6, 7 vehicles monthly, a throughput rate representing merely 4.1% of projected military requirements. The company manufactured 2,675 Jeeps total before War Production Board. Administrators reallocated their contracts to trailer production, a strategic decision prioritizing manufacturing capacity over innovation origination. This represented industrial Darwinism in compressed timeframe, creative primacy subordinated to productive capacity, idea generation valued less than execution scalability. Ford's integration into Jeep production demonstrated the multiplicative power of existing industrial infrastructure applied to standardized designs. The Rouge complex in Dearborn, Michigan encompassed 2,000 acres with 93 structures containing 7 million square feet of manufacturing space powered by the world's largest electrical generation plant, producing 321,000 kilowatts. This infrastructure enabled Ford to achieve peak monthly Jeep production of 28133 units in March 1944, representing 49.7% of total Allied Jeep output during that period. The comparative productivity metrics revealed infrastructure's primacy. Ford's per worker monthly output averaged 3.14 Jeeps compared to Willys' 1.89, a differential attributable primarily to capital equipment density rather than labor efficiency. Ford deployed 2.7 machine tools per worker versus Willys' 1.4. The systemic outcome transcended individual corporate achievement. Combined production from Willys, Ford and supplementary contractors reached 6,39245 vehicles by August 1945, creating logistics infrastructure supporting 16.1 million military personnel deployed across 4 major theaters and 37 secondary operational zones. The Toledo Jeep production line represented a single node within a continental-scale industrial network whose aggregate output revealed systemic capacities that fundamentally altered strategic calculations governing modern warfare. To comprehend the full scope of American wartime production requires situating the 50708 Jeeps manufactured at Willys-Overland within the broader architecture of military-industrial mobilization spanning 1942 through 1945. The statistical landscape defies intuitive comprehension. 6,39245. Total Jeeps across all manufacturers. 2382311. Trucks of various classifications. 88410 tanks, representing 14 distinct model variants. 324750 aircraft encompassing fighters, bombers, transports and reconnaissance platforms, plus 5425 naval vessels, displacing a combined 52.1 million tons. These figures transcended mere production tallies to represent the materialization of industrial capacity, operating at scales previously confined to theoretical projection rather than empirical observation. The synchronization mechanisms coordinating this distributed manufacturing ecosystem demonstrated organizational complexity, approaching biological systems in their adaptive resilience. The War Production Board established January 1942 Administered resource allocation protocols governing 18539 prime contractors and an estimated 450000 subcontractors distributed across 48 states. Raw material flows followed optimization algorithms, balancing competing demands. Aluminum production increased from 412,000 tons annually in 1941 to 256,700 tons in 1943. Yet allocation protocols ensured aircraft manufacturers received priority, consuming 87% of output, while automotive producers adapted designs utilizing steel components where aluminum had previously dominated. This represented real-time reconfiguration of supply chain architecture, responding to strategic priority shifts measured in weekly rather than annual timeframes. The Toledo facility's integration within this network illustrated micro to macro scaling principles. Each Jeep required 2,340 pounds of steel sourced from mills operating at 95.2% capacity utilization, compared to peacetime averages of 61% delivered via rail transport, averaging 847 miles from primary suppliers in Pittsburgh, Cleveland, and Gary, Indiana. Rubber components, tires, seals, hoses consumed 147 pounds per vehicle, necessitating synthetic rubber production. Given that Japanese conquest of Southeast Asian territories eliminated 97% of natural rubber supplies by March. Ichenjo by Sashar, the synthetic rubber program scaling from zero production in 1941 to 75,300 tons in 1944, demonstrated industrial pivot capabilities, addressing supply chain disruptions through technological substitution rather than strategic resource competition. Temporal analysis revealed acceleration patterns suggesting exponential rather than linear capacity growth. January 1942 combined Jeep production from all manufacturers totaled 4,847 units. By January 1943, monthly output reached 28,119, a 480% increase. Peak production occurred March 1944 at 3,1503 vehicles, monthly representing daily output of 1,016 Jeeps, when averaged across 31 days or one vehicle, emerging from the collective American industrial apparatus every 85.1 seconds across 24-hour continuous operations. This production velocity created replacement rates exceeding battlefield attrition by factors of 7 to 1, generating surplus capacity that enabled stockpiling reserves and lend-lease transfers to Allied forces. The Soviet Union received 5,153 Jeeps, Britain 30897, Free French Forces 12441. The economic magnitude underlying this industrial mobilization revealed resource commitment unprecedented in peacetime contexts. Federal defense expenditure in 1944 totaled $79.1 billion, representing 37.8% of gross domestic product, compared to 1,940 military spending of $1.7 billion, constituting 7% of GDP. This 22-fold increase in absolute terms and 22-fold increase in proportional allocation occurred within 48 months, demonstrating fiscal capacity mobilization, matching industrial output, scaling. The Jeep program specifically consumed $386.9 million in direct manufacturing costs, translating to $605 per vehicle. A unit cost 14.7% above initial procurement estimates, but 23.2% below projected inflation-adjusted costs, suggesting learning curve efficiencies compensated for wartime material price escalation. When armistice declarations suspended hostilities in August 1945, the cessation of production created an industrial silence more profound than any acoustic phenomenon. The machinery did not gradually wind down. It stopped a binary transition from maximum operational tempo to complete stillness, executed across 127 Jeep production facilities within 72 hours of VJ Day. Announcement. The post-armistice period revealed an unexpected phenomenon: the persistence of demand curves that military procurement officers had assumed would collapse with hostilities termination. Soldiers returning from European and Pacific theaters expressed acquisition intent for vehicles matching the specifications of equipment they had operated under combat conditions. Willys-Overland market research conducted August through November 1945 via surveys distributed to 14847 demobilizing personnel documented that 67.3% of respondents indicated purchase interest in a civilian variant maintaining core Jeep characteristics, four-wheel drive capability, ground clearance exceeding 8.5 inches, engine torque profiles suitable for gradient climbing and heavy load towing. This constituted a market segment that had not existed prior to 1941. The civilian automotive landscape had been dominated by sedan configurations, prioritizing passenger comfort and highway velocity over off-road capability. Yet military experience had created consumer preference architecture, valuing utility over refinement, mechanical simplicity over aesthetic sophistication, operational reliability over performance specifications optimized for paved infrastructure. Willys executives recognized this represented not merely a temporary post-war anomaly, but a fundamental shift in consumer demand topology. The CJ2A model, introduced July 1945, with CJ designating civilian Jeep, represented strategic product positioning, translating military specifications into consumer markets. The vehicle retained 73% component commonality with the MB military variant identical Go Devil engine, producing 60 horsepower, same Dana Spicer transfer case and axle assemblies, unchanged 80-inch wheelbase. Modifications addressed civilian regulatory requirements and comfort expectations. Tailgate addition for cargo accessibility. Side-mounted spare tire passenger seat, incorporating basic cushioning rather than military canvas. Retail price established at $1,090 positioned the CJ2A at premium tier relative to conventional automobiles, but remained accessible to middle-income consumers, particularly agricultural operators and rural residents for whom off-road capability provided functional rather than recreational value. Production data from 1946 through 1949 validated the market assessment. Willys manufactured 21470 CJ2. Units across this period, with demand concentrating in regions characterized by unpaved road infrastructure and agricultural economies, rural Midwest mountain states, agricultural regions of California and the Pacific Northwest. The vehicle found application beyond anticipated consumer markets. Utilities companies deployed Jeeps for power line maintenance across terrain inaccessible to conventional service vehicles. Forestry services utilized them for fire prevention. Patrol geological survey teams adopted them for field research in remote locations. The cultural semiotics transcended functional application. The Jeep evolved into symbolic representation of a specific historical moment when industrial capacity aligned with existential necessity, when production velocity transformed abstract patriotic sentiment into tangible material contribution. Veterans who had operated these vehicles across North African deserts, European forests, and Pacific islands maintained emotional connections to the machinery that had facilitated survival. The civilian Jeep became memorial object, not commemorating loss, but celebrating endurance, mobility, and the industrial capacity that had enabled victory through material abundance. Every 4 minutes, this temporal measurement repeated across 5 days of sustained production operations, accumulated into something beyond mere quantitative achievement. The 50708 Jeeps manufactured at Toledo between January 1942 and August 1945 represented not vehicles but materialized expressions of organizational capacity. The conversion of abstract industrial potential into deployable strategic advantage, measured in tons of processed steel, thousands of precision-machined components, millions of discrete human actions, synchronized through temporal protocols, calibrated to intervals of 240 seconds. The mathematics underlying this achievement revealed fundamental principles about technological systems operating under constraint conditions that transcend specific historical contexts. When confronted with existential necessity, Industrial infrastructure demonstrates adaptive capacities exceeding peacetime operational parameters by factors that invalidate incremental improvement models. The transformation from Willys-Overland's peacetime output of 3,1000 civilian vehicles annually to wartime production of 5,0708 military vehicles across 44 months represented not linear scaling, but systemic reorganization, retooling workforce, restructuring supply chain reconfiguration, and temporal optimization protocols generating throughput increases of 327%, while simultaneously improving quality control metrics and reducing per-unit manufacturing time from 14 hours to under 6 hours. Yet, the enduring significance resided not in production statistics, but in demonstrated proof that democratic industrial systems possessed latent capacities surpassing authoritarian command economies, specifically because decentralized decision-making enabled rapid adaptation to changing operational requirements. The Jeep production network's ability to integrate 3 competing manufacturers, 847 subcontractors, and distributed workforce exceeding 94000 personnel, while maintaining component interchangeability to tolerances of 0.001 inches, demonstrated organizational resilience impossible within centrally planned systems lacking feedback mechanisms, enabling real-time optimization. The workers who executed this industrial mobilization understood their contribution transcended individual vehicle assembly. Each torque wrench calibrated to specification, each weld inspected for penetration depth compliance, each fastener thread pitch verified against engineering drawings constituted incremental resistance against ideological systems, denying human agency and individual dignity. The assembly line became battlefield analog, not through metaphor but through functional equivalence. Democracy defended itself, not merely through armed force projection, but through capacity to generate material abundance at scales that made victory mathematically inevitable. War transforms nations through violence, but sustained industrial effort, coordinated across millions of individual actions, aligned toward common purpose, transforms history itself. The 4-minute rhythm that defined Toledo operations from 1942 through 1945 measured something more profound than production tempo. It measured the pulse of collective determination, converting abstract ideals into manufactured reality, proof that freedom's greatest weapon was not destruction, but creation.